A molten salt reactor is a class of nuclear fission reactors in which the primary nuclear reactor coolant, or even the fuel itself, is a molten salt mixture. MSRs run at higher temperatures than water-cooled reactors for higher thermodynamic efficiency, while staying at low vapor pressure. The nuclear fuel may be solid or dissolved in the coolant itself. In many designs, the nuclear fuel is dissolved in the molten fluoride salt coolant as uranium tetrafluoride. The fluid becomes critical in a graphite core, which serves as the moderator. Solid fuel designs rely on ceramic fuel dispersed in a graphite matrix, with the molten salt providing low-pressure, high-temperature cooling. The salts are much more efficient than compressed helium at removing heat from the core, reducing the need for pumping and piping and reducing the size of the core. Although the concept is not new, there has been a renewed interest in the technology along with other generation IV reactor technologies. The early aircraft reactor experiment was primarily motivated by the small size that the design could provide, while the molten salt reactor experiment was a prototype for a thorium fuel cycle breeder reactor nuclear power plant. One of the generation IV reactor designs is a molten salt-cooled, molten-salt fueled reactor. The initial reference design is 1000 MWE. History: aircraft reactor experiment. Extensive research into molten salt reactors started with the U.S. aircraft reactor experiment in support of the U.S. aircraft nuclear propulsion program. The A was a 2.5 MWth nuclear reactor experiment designed to attain a high power density for use as an engine in a nuclear-powered bomber. The project included several reactor experiments, including high-temperature reactor and engine tests, collectively called the heat transfer reactor experiments. HTRE-1, HTRE-2 and HTRE-3 at the National Reactor Test Station, as well as an experimental high-temperature molten salt reactor at Oak Ridge National Laboratory. The A used molten fluoride salt NaFZrF4UF4 as fuel, was moderated by beryllium oxide, used liquid sodium as a secondary coolant, and had a peak temperature of 860 degrees Celsius. It operated for 100 MW hours over 9 days in 1954. This experiment used Inconel 600 alloy for the metal structure and piping. After the A, another reactor was made critical, at the Critical Experiments Facility of the Oak Ridge National Laboratory in 1957 as part of the Circulating Fuel Reactor program of the Pratt and Whitney Aircraft Company. This was called the PWAR-1, the Pratt and Whitney Aircraft Reactor 1. The experiment was run for only a few weeks and at essentially zero nuclear power, but it was a critical reactor. The operating temperature was held constant at approximately 675 degrees Celsius. Like the 2.5 MWTR, the PWAR-1 used NaFZrF4UF4 as the primary fuel and coolant, making it one of the 3 critical molten salt reactors ever built. Molten salt reactor experiment. Oak Ridge National Laboratory took the lead in researching the MSR through 1960s, and much of their work culminated with the molten salt reactor experiment. The MSRE was a 7.4 MWth test reactor simulating the neutronic kernel of a type of epithermal thorium molten salt breeder reactor called the liquid fluoride thorium reactor. The large, expensive breeding blanket of thorium salt was omitted in favor of neutron measurements. The MSRE was located at ORNL. Its piping, core vat and structural components were made from Hastelloy-N and its moderator was pyrolytic graphite. It went critical in 1965 and ran for 4 years. The fuel for the MSRE was LiFBEF2ZrF4UF4. The graphite core moderated it, and its secondary coolant was FLIB. It reached temperatures as high as 650 degrees Celsius and operated for the equivalent of about 1.5 years of full power operation. Oak Ridge National Laboratory Molten-Salt Breeder Reactor. The culmination of the Oak Ridge National Laboratory research during the 1970 to 1976 timeframe resulted in a proposed molten-salt breeder reactor design which would use LiFeBF2THF4UF4 as fuel, was to be moderated by graphite with a 4-year replacement schedule, use NaF/NaBF4 as the secondary coolant, and have a peak operating temperature of 705 degrees Celsius. Despite the success, the MSR program closed down in the early 1970s in favor of the liquid metal fast breeder reactor, after which research stagnated in the United States. As of 2011, update, the ER and the MSRE remained the only molten-salt reactors ever operated. The MSBR project received funding until 1976. Inflation adjusted to $1,991, the project received $38.9 million from 1968 to 1976. The following reasons were cited as responsible for the program cancellation. The political and technical support for the program in the United States was too thin geographically. Within the United States, only in Oak Ridge, Tennessee, was the technology well understood. The MSR program was in competition with the fast breeder program at the time, which got an early start and had copious government development funds being spent in many parts of the United States. When the MSR development program had progressed far enough to justify a greatly expanded program leading to commercial development, the AEC could not justify the diversion of substantial funds from the LMFBR to a competing program. Oak Ridge National Laboratory denatured molten-salt reactor in 1980. The Engineering Technology Division at Oak Ridge National Laboratory published a paper entitled Conceptual Design Characteristics of a Denatured Molten-Salt Reactor with Once-Through Fueling. In it, the authors examine the conceptual feasibility of a molten-salt power reactor fueled with denatured uranium-235 and operated with a minimum of chemical processing. The main priority behind the design characteristics is proliferation resistance. Lessons learned from past projects and research at ORNL were taken into strong consideration. Although the DMSR can theoretically be fueled partially by thorium or plutonium, fueling solely on low-enriched uranium helps maximize proliferation resistance. Another important goal of the DMSR is to minimize R&D required and to maximize feasibility. The Generation IV International Forum includes salt processing as a technology gap for molten-salt reactors. The DMSR requires minimal chemical processing because it is a burner design as opposed to a breeder. Both experimental reactors built at ORNL were burner designs. In addition, the choices to use graphite for neutron moderation, and enhanced hastelloy N for piping simplify the design and reduce R&D needed. Russian MSR research program in Russia. A molten-salt reactor research program was started in the second half of the 1970s at the Kurchatov Institute. It covered a wide range of theoretical and experimental studies, particularly the investigation of mechanical, corrosion and radiation properties of the molten salt container materials. The main findings of completed programs supported the conclusion that there are no physical nor technological obstacles to the practical implementation of MSRs. A reduction in activity occurred after 1986 due to the Chernobyl disaster, along with the general stagnation of nuclear power and nuclear industry. Britain's molten-salt reactor program. While Alvin Weinberg's MSR work at Oak Ridge progressed in the US, Britain's Atomic Energy Research Establishment were developing an alternative MSR design across its national laboratories at Harwell, Culham, Risley and Wimfrith. AERE decided that there would be little to gain from replicating ORNL's work, so they opted to focus on a lead-cooled 2.5 GWE molten-salt fast reactor concept using a chloride salt. also researching the option of using helium gas as an alternative coolant. The UK MSFR would be fueled by plutonium, a fuel considered to be free by the programme's research scientists, who viewed the UK's plutonium stockpiles as an asset rather than a liability. Despite developing quite different designs, ORNL and AERE seem to have had close contact during this period, with information exchange and expert visits taking place. Theoretical work on the concept was conducted between 1964 and 1966, and experimental work was ongoing between 1968 and 1973. The program received government funding of around £100–200,000 annually. This funding came to an end in 1974, partly due to the success of the prototype fast reactor at Dounreay, which was considered a priority for funding as it went critical in the same year. AERE reports and findings from its MSR program conducted in the 60s and 70s are available for public viewing at the UK National Archives, in Kew, London. Recent developments. A study on MSRs completed in July 2015 by Energy Process Developments Limited gives an up-to-date summary of MSR activity internationally. It looks at the feasibility of developing a pilot-scale demonstration MSR in the UK. A review of potential UK sites is given along with an insight into the UK regulatory process for innovative reactor technology. The technical review of 6 MSR designs led to the selection of the Molten-Salt reactor as most suitable for UK implementation. MSR review. Molten-Salt waste burner. Seaborg Technologies, a company based in Denmark, has recently been developing the core for MSW. The MSW is a high-temperature, single-salt thermal MSR designed to go critical on a combination of thorium and nuclear waste from conventional nuclear reactors. Thorium produces much less of the long-lived and problematic transuranic waste than conventional reactor fuel, even when running a closed fuel cycle. As a consequence, the core produces much less transuranic waste than it consumes, hence a waste burner. The MSW design is modular and the reactor core is estimated to be replaced every 6 to 10 years. However, the fuel will not be replaced and will burn for the entire power plant lifetime. The first version of the Seaborg core is planned to produce 50 MWth power and is shown to reduce the amount of transuranic waste in the world by approximately 1 ton over its 60 years power plant lifetime. After 60 years, the 233 U concentration in the fuel salt is high enough to initiate a closed thorium fuel cycle in the next generation power plant. White paper. Denatured Molten-Salt Reactor. Terrestrial Energy Inc., a Canadian-based company, is developing a DMSR design called the Integral Molten-Salt Reactor. The IMSR is designed to be deployable as a small modular reactor and will be constructed in 3 power formulations ranging from 80 to 600 MWth. With high operating temperatures, the IMSR has application in industrial heat markets as well as traditional power markets. The main design features include neutron moderation from graphite, fueling with low enriched uranium, and a compact and replaceable core unit. The latter feature permits the operational simplicity necessary for industrial deployment. Liquid salt very high temperature reactor. As of September 2010, update. Research was continuing for reactors that utilize molten salts for coolant. Both the traditional molten-salt reactor and the very high-temperature reactor were selected as potential designs for study under the Generation 4 initiative. A version of the VHTR being studied was the liquid salt very high-temperature reactor, also commonly called the Advanced High-Temperature Reactor. It is essentially a standard VHTR design that uses liquid salt as a coolant in the primary loop, rather than a single helium loop. It relies on TRISO fuel dispersed in graphite. Early AHTR research focused on graphite would-be in the form of graphite rods that would be inserted in hexagonal moderating graphite blocks. But current studies focus primarily on pebble-type fuel. The LSVHTR has many attractive features, including the ability to work at very high temperatures, low-pressure cooling that can be used to more easily match hydrogen production facility conditions, better electric conversion efficiency than a helium-cooled VHTR operating at similar conditions, passive safety systems, and better retention of fission products in the event of an accident. This concept is now referred to as fluoride salt-cooled high-temperature reactor. Liquid fluoride thorium reactor. Reactors containing molten thorium salt, called liquid fluoride thorium reactors, would tap the abundant energy source of the thorium fuel cycle. Private companies from Japan, Russia, Australia and the United States, and the Chinese government, have expressed interest in developing this technology. Advocates estimate that 500 metric tons of thorium could supply all U.S. energy needs for 1 year. The U.S. Geological Survey estimates that the largest known U.S. thorium deposit, the Lemhi Pass district on the Montana-Idaho border, contains thorium reserves of 64,000 metric tons. Fuji Reactor. The Fuji MSR is a 100 to 200 MWe LFTR, using technology similar to the Oak Ridge National Laboratory reactor. It is being developed by a consortium including members from Japan, the US, and Russia. It would likely take 20 years to develop a full-size reactor, but the project seems to lack funding. Chinese project. Under the direction of Jiang Menheng, the People's Republic of China has initiated a research project in thorium molten-salt reactor technology. It was formally announced at the Chinese Academy of Sciences annual conference in January 2011. The plan was to build a tiny 2 MW plant using liquid fluoride fuel by the end of the decade, before scaling up to commercially viable size over the 2020s. It is also working on a pebble bed reactor. The proposed completion date for a test 2 MW pebble bed solid thorium and molten salt cooled reactor has been delayed from 2015 to 2017. The proposed test thorium molten salt reactor has also been delayed. Indian research. Ratan Kumar Sinha, chairman of Atomic Energy Commission of India, stated in 2013, India is also investigating molten salt reactor technology. We have molten salt loops operational at BARC, U.S. companies. Kirk Sorensen, former NASA scientist and chief nuclear technologist at Teledyne Brown Engineering, has been a long-time promoter of the thorium fuel cycle, coining the term liquid fluoride thorium reactor. In 2011, Sorensen founded Flib Energy, a company aimed at developing 2050 MW LFTR reactor designs to power military bases. Another startup company, Transatomic Power, has been created by Ph.D. students from MIT including Drive, Leslie Dewan, CEO, and Russ Wilcox of E-Inc. They are pursuing what they term a waste-annihilating molten salt reactor, focused on the potential to consume existing nuclear waste more thoroughly. Transatomic received venture capital funding in early 2015. The Alvin Weinberg Foundation. The Alvin Weinberg Foundation is a British non-profit organisation founded in 2011, dedicated to raising awareness about the potential of thorium energy and LFTR. It was formally launched at the House of Lords on 8 September 2011. It is named after American nuclear physicist Alvin M. Weinberg, who pioneered thorium molten salt reactor research. European development. The EVOL project, with the objective of proposing a design of the MSFR, released its final report in 2014. The various molten salt reactor projects like FHR, MOSART, MSFR, and TMSR have common themes in basic R&D areas. According to a 2014 paper giving an overview of the MSR in a GENV context, another paper gives an overview of the MSFR. More resources are available in the MSFR bibliography. Molten salt fueling options. The thorium-fueled variant called the liquid fluoride thorium reactor has been very exciting to many nuclear engineers. Its most prominent champion was Alvin Weinberg, who patented the light water reactor and was a director of the U.S.'s Oak Ridge National Laboratory, a prominent nuclear research center. MSR can be fueled using enriched uranium-235. MSR can be fueled using fissile material from dismantled nuclear weapons. Molten-salt-cooled reactors. Molten-salt-fueled reactors are quite different from molten-salt-cooled solid-fuel reactors, called simply molten-salt reactor system in the Generation IV proposal, also called MSCR, which is also the acronym for the molten-salt converter reactor design. These reactors were additionally referred to as advanced high-temperature reactors. But since about 2010 the preferred designation is fluoride high-temperature reactors. The FHR concept cannot reprocess fuel easily and has fuel rods that need to be fabricated and validated, delaying deployment by up to 20 years from project inception. However, since it uses fabricated fuel, reactor manufacturers can still profit by selling fuel assemblies. The FHR retains the safety and cost advantages of a low-pressure, high-temperature coolant, also shared by liquid metal-cooled reactors. Notably, there is no steam in the core to cause an explosion, and no large, expensive steel pressure vessel. Since it can operate at high temperatures, the conversion of the heat to electricity can also use an efficient, lightweight Brayton cycle gas turbine. Much of the current research on FHRs is focused on small compact heat exchangers. By using smaller heat exchangers, less molten salt needs to be used and therefore significant cost savings could be achieved. Molten salts can be highly corrosive, more so as temperatures rise. For the primary cooling loop of the MSR, a material is needed that can withstand corrosion at high temperatures and intense radiation. Experiments show that hastelloy and similar alloys are quite suited to the tasks at operating temperatures up to about 700 degrees Celsius. However, long-term experience with a production-scale reactor has yet to be gained. In spite of serious engineering difficulties, higher operating temperatures may be desirable. At 850 degrees Celsius, thermochemical production of hydrogen becomes possible. Materials for this temperature range have not been validated, though carbon composites, molybdenum alloys, carbides, and refractory metal-based or ODS alloys might be feasible.